Hi, gang. This is just a very brief introduction to 7.2 nuclear reactions, and the only subtopics that will be mentioned today is an introduction to the unified atomic mass unit, mass defect, and binding energy. So this little screencast, the only purpose is really to give you those definitions before you move on to other information. So the AMU is an atomic mass unit, and it's basically what we need to use when we're talking about really, really small quantities. Grams and kilograms just really don't work anymore. So if you're looking at a periodic table and you're looking at carbon, for example, one of the most basic elements that's everywhere, carbon has an atomic mass of 12. That usually means that there's 6 protons and 6 neutrons, both known as nucleons, in the nucleus. But if you're looking at a single carbon atom and you divide its mass, one carbon atom is going to be super tiny. And if you divide its mass by 12, you're going to get what's essentially 1 AMU. Okay, so one carbon atom has 12 nucleons. And on average, each of them, protons and neutrons, weighs about this many kilograms, which is really, really tiny. Okay. It's going to become pretty interesting later in that you can express an AMU in terms of kilograms, but you can also express an AMU in terms of mega electron volts per speed of light squared. And that is because we're about to learn that mass and energy are equivalent through a very famous equation, E equals mc squared, that I'm sure you've heard of. So at the very least, you should get the definition of an AMU written down in your notes. And it is defined as 1/12 of the mass of a carbon-12 atom, okay? The next thing that you're going to learn about today is something called the mass defect and nuclear binding energy. And this has a lot to do with why nuclear reactions release so much energy. So here's something interesting. It turns out that if you take the mass of an entire atom that includes its protons and its neutrons in the nucleus, and then you take that atom apart and you weigh all of the same constituents separately, those masses are slightly different. They are not identical. So how can we make sense of that? So it turns out that that difference in mass is called a mass defect. And because you need to put energy in to remove nucleons from a nucleus, the sum of the energy contained in the separate nucleons, the separate protons and neutrons, is higher than that of the nucleus when it was all put together. And so you can literally get all of the masses of the protons and neutrons separately, and then get the mass of the entire atom when it's all together, and you'll see that's slightly different. And the difference in that mass is called the mass defect. And the difference in that mass is also equal to the amount of energy needed to pull apart that nucleus or those nucleons from each other. Kind of interesting. Very, very closely related is something called the nuclear binding energy. And that's basically what it takes to strip or remove a nucleon from the nucleus of a particular atom. I read something funny that said it's sort of like trying to take a piece of candy away from a stubborn child, which is strange. But if you're literally trying to kind of pull a nucleon away from a nucleus, it takes energy to do that. And that is the energy that ultimately is released when we fission atoms in nuclear fuel, which is kind of interesting. So we often talk about the binding energy as an average amount of energy per nucleon, per whatever it is you're trying to remove, okay? So the binding energy per nucleon equals the binding energy of the entire nucleus divided by the number of nucleons in that nucleus, which makes sense. Remember, nucleons is just a fancy word for protons and neutrons together. Here's that famous equation that you've heard of. Energy equals mass times speed of light squared. That's where this comes in. So energy is going to be in joules or kilojoules, or if we're dealing with one atom, it might be in mega electron volts. Mass is going to be in kilograms, most likely, and then you know that the speed of light squared is going to be in meters per second, and those units are going to be squared as well. Okay, so it's kind of interesting. Down here, this is a pretty famous curve, and I'm going to shrink it down a little bit. This is called the binding energy curve. And so if we were to take a whole bunch of different atoms, starting with hydrogen, hydrogen only has one nucleon. It has one proton and nothing else in there in the nucleus. So it really has it's pretty easy. It doesn't take a lot of energy to remove that nucleon, because you remove the whole atom. That's all you got to do. So many other atoms have a higher and higher and higher amount of binding energy. There's a little dip here, but you can see nickel, iron, two different isotopes of iron have 8.8 mega electron volts binding energy per nucleon. And so when you fuse these smaller atoms together, you get an energy release. And nuclear fusion is a very legitimate type of nuclear reaction. Notice the binding energy climbs up higher and higher and higher until it literally peaks at iron. The nucleons of iron are most tightly bound. It takes the most energy to strip any nucleons from this type of atom. So it turns out that everything kind of leading up to iron with its maximum binding energy, these are the things that are going to do fusion. These are the smallest atoms on the periodic table. And then when you go to the right of iron, you'll see that the binding energy drops sort of gently down to uranium, which is a very famous nuclear fuel that we use. Everything really after iron, these are very large atoms, and what they're going to do to seek stability is split or fission. That's what fission means, when a big atom splits into two smaller elements. So kind of interesting there, and it's something that we will make use of later on. And that is really the intro to these terms that you'll need to know. So make sure you write down the definitions. Thank you.